So yeah, good morning, good afternoon, good evening, everyone. Today, I'm excited to share what my team has been working on. So my talk is titled Africa Reassembled, and we're using AI and modern seismic techniques to map the heating structure of Africa's lithosphere. We're putting the continent's deep layers back together, vertically layer by layer, and horizontally across its wide and complex terrains. So I've broken the talk into three quick parts. The surface view, I'll show a new model of Africa's crust and its regionalization. The upper mantle view, we'll look layers below the crust with a wave noise removal method, and deep learning breakthroughs. I'll give a short demo of two new models, AkiNet and IRADNet. So first, we'll build a new crustal classification for Africa with machine learning on ambient noise. So when we look at a geological map, we see a patchwork of rock ages. The image in the middle shows this pattern: ancient cratons, younger terrains, and rifted edges. Africa is a classic example of this variety. But to understand what's happening beneath the surface, we often turn to geophysical maps. The key point here is that every one of these maps depend on the quality of our seismic models of the crust and mantle. If these models are wrong, our geological story is incomplete. So for much of Africa, the crustal seismic models we have are inadequate. That gap is what our work is meant to fill. We call our tool ADAMA. That's a data set and model assessment of Africa's lithosphere. ADAMA isn't just another model, but it is a continental model built from the ground up. First, we gather a huge set of waveforms. As you can see there on the left, the time station plot, almost 1 million daily seismograms from every station that has operated in or near Africa for the last 40 years. And on the right, you see the station map showing our data coverage over key tectonic features, where here I've highlighted the cratons. So we begin with a huge set of ground motion records that every station in Africa has collected. And by comparing vibrations from every station pair, we can trace out Rayleigh and Love surface waves across the entire continent. If you look at the panels in the bottom left and the bottom right, you see these surface waves. These are the most detailed measurements yet, especially for the short period Love waves that are notoriously hard to identify. And our goal in showing this slide is to give you a taste of Africa whole. So with these measurements, we use probabilistic imaging to build a seismic velocity map. If you look at the left panel, that's the velocity model. And on the right, you see the imaging process in action. The algorithms scan the crust, estimating the wave speeds. And because the method is probabilistic, it also produces an error map. The error map in the bottom right shows where our data are dense and the model robust. Darker colors indicate areas of lower confidence, and so we should be more cautious here. These error maps let us judge the overall fidelity of our final model. So now that we have a continent-wide velocity model, the big question is, what does it tell us about Africa's evolution as a whole? So our plan is to turn that 3D model on the left into a 2D image on the right. In this 2D image, each vertical slice is a 1D velocity profile taken from a unique spot on the map on the left. And if you look at this final image on the right, you see it's a random jumble. There's no obvious pattern or insight. We will feed this unordered image into a machine learning algorithm that will uncover the heating structure and help us build a new crustal taxonomy. So the algorithm we use is called a sequencer, and it's a tool that turns chaos into order. If you look at the three panels, you see how it works. On the left, a clear picture of Einstein. In the middle is the same picture, but the rows of pixels have been shuffled randomly. On the right is the result after sending that jumbled image into the sequencer. By comparing how the adjacent rows match, the sequencer rebuilds the original image perfectly. In short, it discovers the heating structure. So we used the sequencer on our Adama seismic model in the same way. If you look at the bottom panel on the left, that's the disordered low information image. And in the top panel, just right above it, is the same data after sequencing. Patterns appear instantly. We then use k-means clustering on the sequenced image, splitting Africa into two distinct crustal types, primitive and modified. The modified crust derives from the primitive type and keeps the strong glossy gradients at the shallowest and the deepest parts of the crust. When we plot these two classes on a map, their spatial distribution follows tectonic boundaries and is very compelling. On the right, I'm showing you again Adama's new data-driven classification. And then if you look on the left, you see tectonic and geological patterns from a separate geological study. We did not put these two together. They're not derived from each other. So the two maps align strikingly. And what I wanted to note is that these correlations that you're seeing just right before you are absent in earlier global crustal taxonomies. So that match to Africa's rich tectonic fabric shows that Adama contains fundamentally new information about crustal structure and evolution. One last thing, Adama is open source. You can use it. It's a baseline data set that the community can now use to answer key questions about Africa's diverse terrains, cratons, rifts, basins, and mountains. We can now finally study Africa whole by looking at its constituent parts. Okay, so having defined a new crustal taxonomy, I will now shift my focus from the shallow lithosphere into the mantle. Our next step is to explore the origin and meaning of Africa's upper mantle stratification. To ground our discussion, let's revisit Jordan's isopycnic hypothesis. The hypothesis says that the deep continental mantle beneath ancient cratons is melt depleted and therefore buoyant. On the left, you can see this density comparison. At standard conditions, continental rocks are lighter than oceanic rocks. At mantle conditions, the rocks are now in balance because continental rocks have cooled longer. Thus, continents sit on thick, cool, buoyant roots. In this elegant framework, the continent is a single stable layer called the lithosphere. If you look at the left-hand plot, this is a decade-old seismic observation that uncovers a sharp discontinuity within continental lithosphere. This finding seems to clash with the classical view of a thick, stable continental lithosphere that I just elaborated. The usual explanation is metasomatic alteration or partial melting, which breaks the long-term stability. Well, but one key issue here is that to better image this feature, we need high-frequency waves. However, these waves are riddled with echoes and reverberations that mask the deeper signal. Our goal is to uncover and overcome this imaging challenge. With that, we can have robust seismic observation and better test models of continental stratification. So on the top panel, you see raw receiver function observations plagued by noise and reverberation echoes. And we will remove this noise with crisp RF, clean receiver function imaging via sparse radon filtering. The core idea is that the radon transform takes the data on the top, and as a mathematical lens, it rotates the data into the parameter space M in the middle. The transform cleanly separates primaries from multiples. We then run a filter, that's that diagonal line, retaining only the primary coefficients, and then do an inverse transform to transform the data back into the data space, producing a denoised receiver function image. Compare the raw receiver function on the top to the clean receiver function in the bottom, and we are ready to then apply this technique to every African station shown in the map on the bottom left. So here are raw African residual functions before and after CRISP-RF. The raw data are messy, echo-dominated, the primaries buried in reverberations. After CRISP-RF, the image is clean, sharp, coherent across the entire stack. Because we're using high-frequency waves, the cleaned arrivals are not blurred. We recover classic discontinuities seen by previous studies, but we also uncover a new class of discontinuities, double discontinuities. They appear as a velocity increase above or below the typical velocity drop that has been seen before. The clean African data stack is now ready for interpretation. So first, we cross-reference our new observations with published thermal and chemical models. On the left, we are observing that most discontinuity within the craters lies shallower than the melting zone. The mantle is too cold and too depleted for melt. However, single and double discontinuities, if you focus on panel B and E, seem to be able to support active melt. Well, the key takeaway here is partial melting cannot be the primary explanation, especially in cratons, but a subsolidus solid-state process like grayscale relaxation might be plausible. Okay, so classical seismic algorithms like I've shown here, residual function and radar migration, have formed the bedrock of the science I've explained today. So in the last few minutes, I'll explain how deep learning, a type of AI, is now being woven into the same framework, turning the raw waveforms into smart inputs that dramatically accelerate and refine these traditional algorithms. First, Akinet. This is Akinet. It is a physics-informed neural network and extracts wave dispersion from noise correlation. Both the network architecture and the loss function are built to respect Aki's solution to the wave equation for stochastic vibrations and prior knowledge of Earth structure. And what's the advantage? Well, the advantage is that instead of needing millions of pre-labeled examples, Akinet can learn directly from the physics. As a result, we can immediately process a brand new data set without any pre-training, giving it remarkable flexibility and power. And here's a side-by-side stress test. On the left is clean Rayleigh wave data against the conventional Aki estimates waveform fitting routine. Akinet performs comparably on the clean data. And on the right is the noisy love wave data, where our results yield far more reliable estimates than the conventional approach. Why does this matter? Accurate love plus Rayleigh dispersion from Akinet can let us build anisotropy-aware models. With anisotropy, we can track rock's internal fabric, providing a rich view of tectonic deformation. So let's now turn to IRADNet. This is a deep algorithm unrolling technique. It takes a conventional iterative migration algorithm that solves the migration problem you're seeing on the top. And each iteration in that algorithm is unrolled into a layer of a deep neural network shown on the left. The AI learns the most efficient way to carry out the calculation, that migration. It automatically discovers the optimal parameters like W, S, and G, and these are the optimal parameters that are necessary to denoise the data and correctly migrate the seismic waves to depth. In future work, we will apply this framework to many other planetary imaging challenges. So there you have it, Africa reassembled layer by layer from its constituent parts. Classical seismic algorithms, together with AI, peeling back the hidden lithosphere and revealing a continent that is both ancient and ever-changing. A big thank you to the National Science Foundation for making this research possible and for supporting the outstanding work and curiosity of my group. Thank you very much for your attention. I'll take questions now.
Wicked. Thank you so much, Tolulope. I have a million questions. I'll leave it to others first. Does anybody else have any questions? I might ask one first if people are still thinking. Going back to the first algorithm, the beginning when you were doing the segmentation of the craton, and you showed the example with the randomization before you do the organization for the Einstein picture. For the example that you had from your ambient noise tomography, do you randomize that, or was that actually just the ordering that they were all And all your 1D velocity structures or signals, do you randomize those first before you feed them in, or are you feeding them as is?
Yeah, so right there, right? So if you look at, is this the figure you're talking about?
Yeah.
Yeah, so we don't randomize them before we start. They are already random. There's no way to know that, say, for example, a pixel within the West African craton is adjacent to one another. There's no way to know before we send it into the sequencer. So what you're seeing after the sequencer is what the machine learning algorithm thinks it should be in terms of the adjacent locations of each pixel. So it has figured out that classification without being told. So if you look at the bottom left, that already looks random. And if you look at the top, it's now placed the vertical columns that are most similar together. Does that make sense?
Yeah, but what happens if you've got a lot of laterally changing heterogeneity? Like
that's
really,
exactly
really
what it's doing. That's what's exactly what it's doing. It is saying to us that, say, for example, if I look closely at, say, the Sahara Metacraton, right, just along the edge, there's lateral heterogeneity as you move from the right to the left, from within the Sahara Metacraton to outside the Sahara Metacraton. But the algorithm is saying, yeah, those two pixels are not the same crust. Okay. Like the yellow and the blue are not the same. Does that make sense now?
Yeah, so that makes, yeah, that's very cool. And I mean, you're only working with ambient noise tomography, or you're not using any?
Yes, we're only working from the model derived from ambient noise tomography. So essentially, we've taken the ambient noise measurements, we've ingested it into existing models to produce a refined model of Africa's crust. So you can think of the Africa Adama as a model that has seen new ambient noise data. Does that make sense?
Yeah. Is there any value in incorporating some earthquake tomography results in there too?
Oh, you bet. Okay. The value in incorporating earthquake is that you see deeper into the lithosphere. So right now, our most best resolution for Adama is in the crust. Right. So below it, there's no update to existing models. And the existing model we derived Adama from, after seeing the data, is litho 1. So if we were to take litho 1 and look at 80 kilometers, it would be similar to Adama. But if you're then to go shallower, they will diverge because litho hasn't seen Adama's surface, ambient noise surface wave data.
Okay, that makes sense. Cool. I see Sasha's got his hand up. Sasha.
Thanks for this great talk. I have a question on part 2, where you analyze the receiver functions. And you brushed over the methods quite quickly. Can you maybe say what exactly the algorithm is doing on the next?
Maybe I ask a more specific question. Is there anything about this that's kind of confusing? Now I know I can explain, but
so I have actually 2 questions. So how
go ahead.
Algorithm working, and then if it is machine learning algorithm, then often we have the problem that it's a black box and we can't.
Yes, exactly. Good.
Whether it's working or not. So how do you do some
2 spectacular questions? So this is CRISPR-F. It is not a machine learning algorithm. At the end, I spoke about IRADNet. IRADNet is the machine learning variant of this algorithm. Okay. But let me speak about this algorithm. This is not machine learning at all. This is just, in the classical view of things, you can think of it as a slant stack or a vespergram or some approach to aligning waveforms so that they optimally stack. That is the fundamental idea. It's no different in that sense. However, it is more robust in the sense that instead of doing that shift stack process in the time domain, we are doing that shift stack process in the frequency domain. And that's what you're seeing with this kind of equations here that have got these like curly Fs. Those are Fourier transforms and with the shift operations in L. Okay, so that's the fundamental idea. And then another extra idea is this actual parameter here. I don't know if you can see my, I'm pointing correctly to it, but well, I'll have to talk you through it. So that like lambda psi m, that is a constraint you are enforcing on the model M in the middle. Essentially, what that says is we know in the Earth that the Earth should be comprised of layers at some wavelength, and those layers should not be many. So because of that a priori information, we're saying, give us models that are sparse. Noise often is non-sparse, so we're going to penalize noise and only look for sparse models. This is this idea of sparsity promotion, CRISPR, sparse radon filters. And so with those 2 ideas and new algorithms for solving sparse problems, we can then translate the data on the top to the model in the middle. So that's CRISPR. It's not novel machine learning in that sense, but it is new in the sense that we're using sparsity as a constraint. Now, the challenge with solving any optimization problem is that you are trying to trade off data fidelity with model fidelity. And there are a bunch of knobs you can tune and that the students kind of suffer through in trying to subjectively decide that that we've gotten the correct model. And so that's what then IRADNet is trying to solve. Does that make sense?
Okay. Yeah, a lot. Thanks.
You're welcome. Thanks for those questions. Very good questions. Oftentimes, I try not to get stuck in this, except for seismologists who care, and or mathematician or signal processing folk. But those are very, very good questions. And as you can see, the flavor of my talk has been to not just give you the science, but to try to go back into the methodology and say, okay, can we do better? Because if we can do better, we can answer new questions.
I'm going to take the opportunity to ask another question since we only have one other speaker and it's recorded.
And this will be your last question, because I have a class in 2 minutes.
Oh, wicked. For the receiver function part, where you show the original and then your crisped up version, I think it's on the next slide. Yeah. So one of the things I usually like about the messier receiver function is my eyeballs can get a little bit more creative, whereas in the lower one, it's really being like sparsified like significantly. For those particular shallow boundaries, do you have controlled source reflections anywhere that you can constrain with this?
So to your concern is we can actually verify some portions of that CRISPR process. So yes, I agree with you that we're not taking the human out of the loop completely. And one of the things we do is to ensure that for existing MOHU models that we think are good, we'll actually predict the arrival time of the phases for the crust and its reverberations. And that ground truths to some degree the CRISPR process. But other than that, we are not going to a priori say, okay, I'm going to visually draw a line to look for coherent phase. We're not going to do that. And so that's what this is. However, we are now writing a global paper that suggests that that process is pretty robust in terms of what we're finding in upper mantle stratification globally. And so again, our goal is to try not to impose human constraints or human bias in the processing as much as we can. We can ground truth it, we can check, but not impose. And then after the fact, step back and ask, okay, what are we learning? But your questions and your concerns are valid. I hope that answers the questions.
It would definitely be cool to apply this to like the EarthScope data where you've got ridiculous amounts of data.
And we've published another paper. So that's the paper I was showing there. So if you look at that slide, it's a triad of papers. Olugbji 2023, that's the method. Carr on Olugbji 2024, that's applied to EarthScope. Huge amount of data, super clean data. Carr and others 2025 applied into the mid-mantle below the transition zone, discovering or unraveling mid-mantle discontinuities in unprecedented detail for EarthScope data, both in the lower 48 and Alaska. And now Legray and Olugbji 2025 in Africa. It's like CRISPR have gone wild.